All right, let's take a look at example 2. So we have a 2 kilogram piece of copper at 200 degrees C. It's taken out of a furnace and is let stand to cool in air with ambient temperature 25 degrees C. Calculate the entropy generation as a result of this process. Additional data, the CP of copper is this, which we can assume is constant. All right, so we're asked to calculate the entropy generation. Okay, so my entropy generation is going to be equal to the change in entropy of my system. Okay, so the change in entropy of my system plus the change in entropy of my surroundings. Okay, so we're going to have to calculate the change in entropy of our system and the change in entropy of my surroundings, where in this case I'll take my system to be my block of copper. Okay, so I'm going to take a hot block of copper out of the oven, and so I'm going to take my system to be copper. All right, and so copper is going to exchange heat with the air that surrounds it. Okay, so I'll take that ambient air to be my surroundings, and since we have copper in some massive atmosphere, I'll assume that my ambient air can be assumed to be a bath, right? So that the temperature of my air is constant. Okay, so it's able to absorb that heat from copper, and the change in the surrounding air is negligible. Okay, cool. Now remember, when we talk about thermodynamics, we're talking about the infinite time limit. All right, so that change in the temperature of the air, after the cooling process has completed and everything's equilibrated. All right, so let's take this piece by piece. Okay, so in my initial state, okay, so again, my system is my copper, my block of copper that's coming out of the oven. Okay, so for my system, all right, so as I calculate delta S of my system, I take this block of copper out of the oven. So the mass of copper is 2 kilograms. The initial temperature of my copper is 200 degrees C. And my final temperature, okay, is going to be 25 degrees C. Okay. Why? Because taking copper out of the oven, it's in contact with ambient air, which is at 25 degrees C. I'm assuming my ambient air, my surroundings, is a heat bath. So I know that my copper or heat will be released from my system until it reaches a final temperature of 25 degrees C, at which point it's in equilibrium with my surroundings. All right, so what's the change in entropy? Okay, so I am going to assume that copper, right? So I have this copper block. So I'm going to assume that I have an isobaric process. Okay, so I'm going to assume that my process is isobaric. Okay, I assume I could, just as well. I'm assuming it's isobaric. I just as well could have assumed that it's isochoric, constant volume. Isobaric makes a little more sense here because I'm given CP. And typically for a solid, we assume that solids are incompressible, right? So isobaric, isochoric will virtually be one and the same. Okay. So I'll assume that my system's isobaric, that copper, the pressure is going to remain constant. Again, I could have assumed isochoric. The difference should be negligible for our solid here. So for an isochoric process, my first law of balance, or isobaric process, my first law of balance reduces to delta H is equal to Q. If it was isochoric, it would be delta U is equal to Q. Okay, so delta H is equal to Q, which would correspond to the integral from my initial to my final state of Cp dt. Again, in differential form, this would be dH is equal to dQ, which is equal to Cp dt. All right, now my definition of entropy is that my change in entropy is equal to my reversible heat exchange divided by T. So for my isobaric process, and ds then is equal to, well, dq Cp dt, so it's going to be Cp over T dt. All right, so now if I want to calculate the change in entropy, and going from 1 to 2, state 1 to 2, okay, and this is for my system, is equal to the integral from 1 to 2 ds, which is equal to the integral from 1 to 2 Cp over T dt. Now in the problem, we're given a value of heat capacity. We're not given temperature dependence, so I'll assume that it's constant. So I'll get that, so I'll bring out Cp, and this could be integral from 1 to 2, 1 over T dt, okay, which leads to delta S of my system from 1 to 2 is equal to Cp log T2 over T1. Okay. Now I have a ratio of temperatures, so again, you need to make sure that you're using absolute units of temperature here, so use Kelvin and not degrees C as we're given. Okay. We'll jump over to MATLAB and compute that in just a second. But I want to note we're also given the mass. So the total extensive entropy, change in entropy, so I'll write total, is just equal to the mass times my intensive entropy, which I've computed here. So I'm just going to write as m Cp log T2 over T1. All right, so go ahead and compute both of them at the same time. So I'm going to jump over here. Okay, and so I'm going to just make a note. So for my system, Cp is given as 0.38. That's kilojoules per kilogram. Kelvin. So T1 is 200 degrees C. I'm going to add 273.15 to it to convert from Celsius to Kelvin. T2 is 25. And my mass, okay, it's in kilograms, which is perfect. All right, Cp is in kilojoules per kilogram Kelvin, so that's going to dictate my units of S as I calculate it here. All right, so when I calculate delta S, okay, the log ratio of temperatures, that's dimensionless, so its units are that of Cp. So the extensive value, when I multiply it by mass, all right, that's great. I'll get kilojoules per Kelvin. All right, mass is in consistent units as here. Okay, so mass is 2. So if I want to calculate ds of my system, that was equal to Cp times the log ratio of my final temperature divided by my initial temperature. And if I wanted my extensive change in entropy, that was mass times, and I'll just write ds system. Okay, so let's save this. So delta S is negative 0.1755. And that's kilojoules per kilogram Kelvin. And my extensive value is a negative 0.3510. And that is kilojoules per Kelvin. All right, now I need to calculate the change in entropy for my surroundings. Okay, so I need to perform an analysis for my surroundings. Okay, so the key is going to be, I'm going to assume that I'm exchanging heat with a bath, right? I'm going to take my ambient atmosphere, ambient air, to be a bath. Okay, so I'm going to assume I have a bath. Okay, and what does that mean to have a bath? It means that essentially the change in temperature of my bath is negligible, right? So I can assume that the temperature of my bath is constant. So, definition of entropy, right, is ds is equal to dq, okay, dq reversible over T. So now when I'm talking about my bath here, this is dq, okay, of my bath, and this is the temperature of my bath. All right, well, what's the heat, what is the heat, absorbed or given up by the bath, right? In this case, I'm going to have a transfer of heat from my hot block to my bath. Why? Because my hot block of copper is at a higher temperature than my bath. So heat's going to flow from my hot block to my bath, ambient air. So the trick to computing the heat of my bath, right, is going to be to replace that with the negative heat of my system. So the idea being any heat released by my system is absorbed by the bath. Right, so d bath I'll replace with negative dq system, and then that's divided by t bath. Okay, cool. Okay, so that essentially I'm going to have delta S of my bath or my surroundings, okay, is going to be equal to negative Q of my system, okay, divided by the temperature of my bath, which is taken to be constant. So in order to calculate this, right, I need Q for my system. Okay, well, what is Q for my system? Okay, we already essentially cooked up the formula up here. All right, so if we assume that we have an isobaric process, then Q for my system is equal to delta H, which is the integral from 1 to 2 Cp dt. Okay, so Q of my system was equal to the integral from 1 to 2 Cp dt, right? Because we assumed constant temperature process for the cooling of our block. Cp is constant, so we get Cp integral from 1 to 2 dt, which is Cp times T2 minus T1. Okay. Now in theory here, you could use degree C, since the difference in degree C is the same as the difference in Kelvin. All right, so then plugging it in, right, delta S of my surroundings will be equal to negative 1 over T bath times Cp T2 minus T1, or I'm going to write it as delta S of my surroundings is equal to Cp over T bath, and I'll use that negative sign just to switch the order here, T1 minus T2. And if I want my extensive value, okay, well, I would just use my extensive Q. All right, so delta S total of my surroundings. Okay, what would differ is SQ of my system here is my specific value, or it's per kilogram. So I would just want the extensive Q. All right, and so to get the extensive Q, I would just take Q system and multiply by mass, the mass of my block. So I would do the same thing here. All right, I can write it as mCp over T bath times T1 minus T2. All right, mass here corresponds to my block. All right, why? Because if I want this to be extensive, I want the extensive Q, all right, which corresponds to the heat released by the block. All right, so let me add a new page. We'll go over to MATLAB again and compute these two, and then see what we have. So for my surroundings, okay, I already have all the quantities I need. T bath, right? So I can, T bath is just equal to what I was calling T2 up there. So ds of my surroundings is going to be equal to Cp divided by T bath times, so now here T bath needs to be in Kelvin, right? Cp divided by T, so you need to make sure that's in Kelvin. Temperature here, I would just keep T1 and T2 in Kelvin. Okay, but you could use degree C since a difference, we're talking about a difference here. Okay, but T bath needs to be in Kelvin. So Cp over T bath times T1 minus T2. Or if I want the extensive value, it's just the mass of my block times that value I just computed. So now this time it's positive. So delta S of my surroundings is 0.2230. That'll be kilojoules per kilogram Kelvin. And the extensive value would be 0.4461. Right, 0.4461, and that is in kilojoules per Kelvin. So then if I want my entropy generation, okay, so let me just write the extensive value. It'd be the extensive change in entropy of my system, so delta S system total plus delta S surrounding total. So my entropy generation would correspond to Sgen total would be delta S for my system total plus delta S for my surroundings total. And that's 0.0951. 0.0951 kilojoules per Kelvin. All right, so you find that Sgen is greater than 0, as we'd expect, right? Sgen has to be greater than or equal to 0. Sgen is equal to 0 for a reversible process. Sgen is greater than or equal to 0 for all other cases, right? So Sgen is greater than 0 for an irreversible process. And so here we have Sgen is greater than 0. Okay, cool. Hope that helps.